somebody had asked if I could talk about another limit definition example. And then also someone asked if I could talk about another left endpoints, right endpoints kind of example. So we'll do one of each of those, and then we will move on and talk about some U substitution, because there's definitely a lot of U substitution on your homework assignments. So let's do a left-right endpoint kind of deal. And so that's kind of all the information I was given. So I would say, let's say we want to estimate the area under f of x equal to x cubed plus 2x plus 1 on the interval from 1 to 5 using, that will be annoying here, n equal to 8 endpoints, n equal to 8 intervals with both left and right endpoints. Now, the actual calculation of this is usually typically terrible, because you have to like plug in your values to your function and get them out. I'm not going to do all that. I'm going to show you how you would calculate it and then kind of move on. And really what I would point out here is we don't need to draw a picture at all. You don't need to draw the function, but what I do really want to draw actually is the x-axis. So I'm going to draw my x-axis, also known as your number line. And I'm going to go from 1 to 5. And I'm going to break that up into 8 subintervals. I guess I could have written subintervals here. Sometimes people go back and forth between saying intervals and subintervals, so it's kind of the same thing. So I'm going to take my b minus a divided by n, and get 5 minus 1 divided by 8, which reduces to 1/2. And that's my base of each rectangle. And I'm going to label things here. I'm going to break this up into 8 subintervals. So I know that each next endpoint is just 1/2 away from the previous one. So the next endpoint here is going to be 1.5, and then 2, and then 2.5, and then 3, and then 3.5, and then 4, and then 4.5, and then 5. Those are all of the ends of my intervals. So if I pretended like I drew my function here, my first subinterval would have a left endpoint of 1 and a right endpoint of 1.5. And my second would have a left endpoint of 1.5 and this right endpoint of 2. And so on and so on and so on, all the way up to my last one would have a left endpoint, my last one being my 8th one, would have a left endpoint of 4.5 and a right endpoint of 5. So if I want to estimate the area using right endpoints, and I should really write that as R8, not Rn, because it's right endpoints using 8 subintervals. I would take each rectangle. Again, this picture is not meant to be accurate in any way, shape, or form. But each rectangle, I would get the height by drawing a right endpoint height. So here's my pretend estimate. I knew I said I wasn't going to draw it, and then I lied. Sorry, I know. Happens sometimes, I just can't help it. That's what it would look like using right endpoints. I don't actually care what it looks like. I care that I can calculate it by saying the base of that first rectangle is 1/2. The height is f of 1.5. The second rectangle has a base of 1/2. The height is f of 2. Each subinterval, I'm using the right endpoint to find the height of the function. And I continue on. F of 2.5, f of 3, f of 3.5, f of 4, f of 4.5, f of 5. Now, if I've done things correctly, how many things should I be adding up? 8. Let's count them. 1, 2, 3, 4, 5, 6. Yep, I did it right. There's 8 things I'm adding up. So good. Now, to actually complete this problem, you'd have to do the annoying work of plugging in 1.5 to your and all these values to your function. So I don't want to do this, but I'll just say if you were doing this, you would get this equal to 1/2 times. It's gross, right? It's going to be 1.5 cubed plus 2 times 1.5 plus 1. And then you go to the next thing, have 2 cubed plus 2 times 2 plus 1. And then you would just keep going until the very last one and get, if you plug in 5 cubed plus 2 times 5 plus 1. I'm not going to do all that. For left endpoints, the process is almost literally exactly the same, except you're going to start at the left endpoint. And so our beginning for L8, which is also an approximation of the area, is going to be 1/2 times f of 1, because we're using the left endpoint of the first subinterval, and then f of 1.5, because we're using the left endpoint of the second interval, and so on. F of 2, f of 2.5, f of 3, plus f of 3.5, plus f of 4, plus f of 4.5, ending on the left endpoint of the last subinterval. Question, Tiffany?
Is there any situation where we have to use like either or?
So here's the thing. Either one is an acceptable estimate of the area under the curve. So if someone just said use 5 subintervals to estimate the area under the curve and didn't say anything else, you could use left endpoints or right endpoints. You could use midpoints, you could use uppers, you could use whatever you wanted if they didn't give you any further instruction. And all of them are valid estimates of the area under the curve, but they are going to be different. So if you use left versus right, you're going to get a different estimate than someone else. And then the idea here is that whichever you use, whether it's left or right or mid or upper or lower, as you let the number of subintervals get larger and larger and larger, each subinterval gets narrower and narrower, and so that all of them eventually approach the same limiting value, which is the area under the curve. That's why it doesn't matter if we use left or right or other endpoints to calculate the area under the curve, at least when we can find the limit. Yeah. They do not have to be equal, but generally we try to let them be equal. So it is usually the case that we make our subintervals all the same. Now, there are problems where it is actually convenient to not do that, but for the most part, the problems we see, we usually let them be equal to each other. Actually, I'll find it later. There's a good example of a function like the square root of x, where if you let the intervals be not equal, you can calculate the area under it using the limit definition, which is kind of neat. Not really that necessary. Other questions about this before we do another limit definition example? Which, yeah, we can do this one. Might as well. All right, so let's, yeah. No, I don't want to do that one. Not because it's terrible, but because it doesn't have all the things I want you to see. So let's find the area under f of x equal to, how terrible should I make this? Not that terrible. 6x squared plus 4x plus 3 on the interval from 1 to, sure, let's go 1 to 3. Now, I'll just point out, we could do, if someone just wrote this and didn't say anything else, you shouldn't do it the long way. Just like in calculus in 17a, if someone said, find the derivative of x to the 4th, and they didn't say using the limit definition, you should just use the power rule and say the derivative is 4x cubed. But we're going to do it both ways here, because I want you to see it the short way and the long way. So the short way, using the fundamental theorem of calculus part 2, the area is just going to equal the integral from 1 to 3 of our function, 6x squared plus 4x plus 3 dx. We're going to anti-differentiate. So we're going to get 6x cubed over 3 plus 4x squared over 2 plus 3x. We do not need and should not write plus c when it's a definite interval. If you do, that's fine, but they're going to cancel out. Because you're going to get a, in fact, I will write the plus c just so you can see that. But I did plus c from 1 to 3. Then I'm going to plug in the 3. Oh, I should simplify first. I should write this as 2x cubed plus 2x squared plus 3x plus c from 1 to 3. And now I'm going to plug in which thing first? The 3. So I'm going to get 2 times 3 cubed plus 2 times 3 squared plus 3 times 3 plus c minus, then I'm going to plug in the 1. You get 2 times 1 cubed plus 2 times 1 squared plus 3 times 1 plus c. Now, it's kind of silly to like show the work of plugging in the 1, because 1 to any power is 1, and whatever constant you have times that is still that constant. So I could have just said, I know when I plug in 1, I'm going to get 2 plus 2 plus 3 plus c. So simplifying this, 2 times 27 is 54, 2 times 9 is 18, 3 times 3 is 9, plus c minus 2 minus 2 minus 3 minus c, distributing that by side. And notably, the c's will always cancel. That's why we don't ever write them when we're doing a definite integral, because they always end up just canceling out when you do the subtraction. So you should never write them when you're doing a definite integral. Finishing this up, 54 plus 18 is 72, plus 9 is 81, minus 2, 2, 3 is minus 7. So you end up with 74. Great. So that's the answer we're hoping to get when we do it the long way. Time for the long way. The long way, hopefully, the long way is the long way. So using the limit definition. And definitely stop me if you have questions or interject. Be like, hey, James, I have a question about that. You're doing something weird. So with the limit definition, I like to start off by writing that the integral from 1 to 3 of my function, 6x squared plus 4x plus 3 dx, is equal to the limit as n approaches infinity of the sum from I equals 1 to n. And now I'm going to fill it in, but I'm just going to point out what's going to go here is our f of x sub I. And what's going to go here is our delta x. Right? What we just did before, we did f of x sub I, the height of our rectangle, times delta x, the base of our rectangle. We still need to find those things in the same sort of way. So I'm thinking about taking my interval from 1 to 3. And now here's the question I feel like is always a little bit hard for people to remember what the answer is to. How many sub-intervals am I breaking up my region into? Say that one more time. You're close. It's going to be n, and then we're going to take the limit as n goes to infinity. So yes, in essence, infinity, but in reality, it's going to be n subintervals. So if I'm going to break this up into n subintervals, well, just like before when I broke the interval from 1 to 5 up into 8 subintervals, I did 5 minus 1 divided by 8 to find the width of each equal length subinterval. So here, my delta x is going to be 3 minus 1 divided by n, which is 2 over n. The x sub I part's always a little bit weird, but basically, your first, I should say, your left endpoint here is your x sub 0. And then each subsequent one is x sub 1, x sub 2, x sub 3, all the way to the last one being x sub n. And each time to find the next one, you're just adding on what delta x is equal to. You don't have to I do this every time to make sure that people are understanding what's happening here, but you don't have to show this work when you're doing this at home. You can just memorize, if you want, the fact that x sub I is equal to a plus I times delta x. X sub 1 is 1 plus I times 2 over n. So I'm starting at 1 and then I'm adding, oh, sorry, not 1, sorry, 1, apologies, 1 times 2 over n. And x sub 2 is 1 plus 2 times 2 over n. And x sub 3 is 1 plus 3 times 2 over n. Right? Every time you go one more delta x to the right, you're adding on one more delta x. So my x sub I is 1 plus I times 2 over n. And I always like to check. When I say check, what I mean is check that x sub 0 is what it's supposed to be, and the x sub n is what it's supposed to be. If you plug in 0 for I, you get 1 plus 0 times 2 over n, which is just 1. If you plug in n for I, you get 1 plus n times 2 over n. N times 2 over n is 2, and 1 plus 2 is 3. Yes. So when x sub 0 is 1 as it should be, and x sub n is 3 as it should be. That means I'm feeling pretty confident that I've done the right thing when it comes to what x sub I is equal to. Hopefully I left myself enough room to write this in here. It's going to be a little bit tight. My f of x sub I, I'm taking the thing for x sub I and substituting it into the function f of x. So it's going to be, it's going to be a little bit close here. So 6 times x sub I squared, so 1 plus 2i over n squared, plus 4 times x sub I, plus 3, just barely. So there's the height of my ith rectangle. I should say the height of the right endpoint of my ith rectangle, because x sub I is definitely the right endpoint of the ith rectangle. Just like x sub 1 would be the right endpoint of the first rectangle. X sub 2 would be the right endpoint of the second rectangle, or I should say when I plug it in. So now the rest is terrible algebra. Not that terrible, but kind of terrible. Questions about anything we've done so far, though? Okay, here we go. So we know we want to get 74. If you did a problem like this and you knew you were supposed to get 74 and you didn't get 74 and it was like on a test, do the work, internalize the fact that you know you made an algebra error somewhere and life is going to go on, and then move on to something else. And if you have time at the end, come back to the problem and try and fix it. But as long as you've done most of the work mostly right, most teachers, that's good, right? They want to see that you know what you're doing. And if you made an algebra error somewhere and got this, like you had a minus sign where you should have had a plus sign and you didn't get the answer you know you should have gotten, that's okay. In fact, if I was asked to do this on the test, I wouldn't do this. I don't want to know that the answer is 74, so that when I get the wrong answer later accidentally, I'm not trying to fix it and spending too much time doing this one problem on the test. So, word of advice. So let's try and calculate this limit as n goes to infinity of the sum from I equals 1 to n of 6 times 1 plus 2i over n squared plus 4 times 1 plus 2i over n plus 3 all times 2 over n. And if you want to save yourself from writing out the limit and the summation every time, just say you're going to deal with the inside stuff for a minute. So let's see, I've got this. I've got 6 times 1 plus 2i over n times 1 plus 2i over n. Here's what I point out, though. I'm not going to say that this is equal to this. They're not the same. I didn't write the limit or the sum. I'm doing some side work right here, just to not have to write out all this garbage every time I'm trying to simplify my expression. So distribute the 4 plus 8i over n plus 3, and that's still all of that times 2 over n. There's all the inside stuff that eventually I'll throw back into the summation once I've gotten into a nicer place. Let's FOIL this out. So I've got 6 times 1 plus 2i over n plus another 2i over n plus 4i squared over n squared. I might as well throw the 4 and the 3 together and say I've got 7 plus 8i over n times 2 over n. Let's distribute the 6. Oh, see, it's a lot of just terrible. So let's see, I've got 6 times 1. I'm going to put these together and say that's 2i over n plus 2i over n is 4i over n. And 6 times that is going to be 24i over n. And then 6 times 4i squared over n squared is going to be 24i squared over n squared plus 7 plus 8i over n times 2 over n. We're almost there. 6 plus 7 is 13. 24i over n plus 8i over n is 32i over n. And 24i squared over n squared. All times 2 over n. Finally, we multiply the 2 over n through, or we distribute, and we get 26 over n plus 64i over n. Whoop, that seems, over n what? Thank you. Plus 24 times 2 is 48i squared over n cubed. I do a quick check. Each of these has a one higher power of n in the denominator than the power of I in the numerator. That is always what I'm looking for. I squared over n cubed, I to the first over n squared, I to the 0th over n to the first. I'm good to go. That is always what I want to see happen. So now we go back and say, okay, so this is now going to equal the limit as n goes to infinity of the sum from I equals 1 to n of this much less terrible looking thing. And then I think we can do two things at once. We can break this up into 3 summations and also pull any constant multiples out in front. I'll do it in 2 steps. So limit as n goes to infinity of the sum from I equals 1 to n of 26 over n plus the sum from I equals 1 to n of 64i over n squared plus the sum from I equals 1 to n of 48i squared over n cubed. And now we can pull out the constants. What's the only thing that doesn't get to count as a constant as far as each of these summations is concerned? Is it the I or is it the n? So let me make sure I phrase it. So which thing is not the constant? Which thing is changing? I, right? We're letting I equal 1, and then 2, and then 3, and then 4, and then 5, and so on. As far as the limit's concerned, n is changing, but I'm not talking about the limit right now. I'm just talking about the summation. As far as the summation is concerned, I is the thing that is changing. So n gets to count as a constant, meaning it can come out as a factor. So I can write this as the limit as n goes to infinity of 26 over n times the sum from I equals 1 to n of 1 plus 64 over n squared times the sum from I equals 1 to n of I plus 48 over n cubed times the sum from I equals 1 to n of I squared. Woof. And then this is where we have to use the formulas. So we're going to say this is the limit as n goes to infinity of 26 over n times, if you add 1 up n times, you get n. 1 plus 1 plus 1 plus 1, n times just n. Plus 64 over n squared times the sum from I equals 1 to n. So 1 plus 2 plus 3 plus 4 plus all the way to n is n times n plus 1 over 2. And finally, 48 over n cubed times the sum from I equals 1 to n of I squared. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to n squared is this unwieldy formula, n times n plus 1 times 2n plus 1 over 6. Okay, here's where I think you get to jump to the end. So let me ask everybody. 26 over n times n is what? 26. Good times. I'm not writing the limit because I'm just writing the answer right now. So if we were to multiply out 64 times n plus 1 over 2n squared, the highest power on the top and bottom would be n squared. It's always going to be the same if we've done things right. What's the coefficient of n squared on the bottom? If you multiply it out? 2. What's the coefficient of n squared on the top if you multiply the whole thing out? 64, right? Because this here, right, that's really n squared plus n. If you distribute the 64, you get 64n squared plus 64n. Okay, finally, and this is the one that's always a little bit weird. Oh, and by the way, right, and then I'm saying the degree on top and the degree on the bottom are the same, so the limit is just the quotient of those leading coefficients, which we talked about last time a little bit. Okay, finally over here, what's the coefficient of n cubed in the denominator? It's not a trick question. If you multiply this out, what would you actually have as the coefficient of n cubed? 6. All right, on top, it's a little bit trickier. It's not just 48, it's 48 times 2. Because if you multiply all this out, you get 2n cubed plus lesser terms, and 48 times 2n cubed is 96n cubed. So the coefficient of n cubed on top is 96. Now I'm really worried this isn't going to come out to be right, because I'm always worried it's not going to come out to be right when I do it the long way. But let's figure out what we've got. We've got 26 plus 32 plus 16. 96 divided by 6 is 16. And that's going to be 58, 68, 74. Yeah. Same answer. So this is the long way. It's not the fun way, but it is the right, not the right, it's the right way if you're doing the limit definition. Okay. Questions about any of that? I'm happy to clarify, expand. You guys are like, no, don't ask any questions. We're done with this. So I see a number of you have some homework due on Friday. Well, I should say those of you that have, because Lee doesn't collect homework, right? Right. So those of you that have homework due to do on Friday, I will mention I posted everyone's homework on Canvas again, and I will try to do that every week. Just so for those of you that are in classes where the homework is not due, you can see more homework questions. I also point out that for those of you that are in Alvarado's class, questions 1 and 5 have some issues that I hope he corrects, because especially question 5 is not really doable because of the domain of the interval. But that's neither here nor there. We'll cross that bridge later on. I sent him an email, so hopefully he fixes the mistakes in the homework.
Alvarado was like, it's 3.
What's that?
But like number 3 is like the integral is like 0, and I was just like,
That happens sometimes.
okay.
But the problem with number 5 is that the integral is from 0 to 9, but the function is only defined when x is between 0 and 1, and that's an issue. So anyway, but we'll get there when we get there. Let's talk. Oh, and I had written myself a note. Yeah. Oh yeah. I have a hand up for this. This is not no there. I had a hand up. Cool. Antiderivative rules. I want you all. Everybody should have one. Take one and pass around. You don't have to take one, I guess, if you don't want one. But take it down, because I do want to add one thing to this list that's not on there that everybody should have. So I'll just start talking about this briefly here. So this is just a list of differentiation rules and anti-differentiation rules, but they're written very generally. So the derivative of x to a power is the power times x to the 1 less power. The antiderivative of x to a power is x to the power plus 1 divided by the power plus 1 plus c, as long as the power isn't -1. The derivative of the natural log of x is 1 over x. The antiderivative of 1 over x is the natural log of the absolute value of x plus c. These are some rules we'll kind of come to later. The derivative of e to the x is e to the x. The derivative of e to the kx is k times e to the kx. The antiderivative of e to the kx is 1 over k times e to the kx. And I'm going to talk about that a little bit more today, so don't stress too much. And then you've got your trig functions. Derivative of sine is cosine. The antiderivative of cosine is sine. The derivative of cosine is negative sine. The antiderivative of sine is negative cosine. The derivative of tangent is secant squared. The antiderivative of secant squared is tangent. I know I'm not saying the k part. I'm just kind of pretending like k is 1 for the moment. The antiderivative of secant squared of 1x is 1 times tangent of 1x. But I want to throw in there, and this is the one that everyone should also add to theirs, because it's one you're expected to know, unfortunately, is that the derivative of the inverse tangent of x is 1 over, how do we like to write this here? It doesn't really matter, but I like to try and be consistent. Sure. It's 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared dx is the inverse tangent of x plus c. And if you want the more general version, the antiderivative of 1 over 1 plus, what do I got here? Yeah, it's k squared x squared dx is equal to 1 over k times the inverse tangent of k times x. Let's see. So this list is, I would say, pretty exhaustive. These, I think, are all the antiderivatives you are expected to be able to know. I know, let me zoom in a little bit here just to make it a little bit easier. That's okay. Good job, James. In case you can't see that very well. Also, just for fun, you could write this as the derivative of the arctangent of x if you prefer. And I kind of do prefer that notation, arctangent. And so the integral of 1 over 1 plus x squared, you could also write as the arctangent of x. It's just a different name for the same function. Question? Like of the other inverse trig functions? I don't believe you do. I'm fairly certain that this is the only one that ever gets asked about, but technically you should ask your instructor, because your instructor might be like, yeah, I'm going to ask you about the function whose antiderivative is arcsine. Arcsecant and arccosecant, I'd be extra surprised if they came up. Arcsine and arccosine, I would be less surprised, but they could come up. No, I've never seen anyone ask about that in this class, at least not by name. Sometimes they kind of sneak it in there by giving it to you without saying it is what it is. But no, I've never seen that in this class. So I would hold on to this. It's a good reference. You should try to kind of get to know these. So let's look at some, let's do some antiderivatives. And then we will definitely do some U sub, I promise. Let's say I want to find the antiderivative of 2 over x minus 1 over x plus 4. And I'm just going to point out, this is how let's zoom back out, James. This is how I'm usually going to write an antiderivative now. I'm not going to be like, the function f of x is this, and the antiderivative is capital F of x. Let's just use the notation that's fairly standard, which is using the integral symbol or the indefinite integral symbol to mean antiderivative. So that just means antidifferentiate. Antidifferentiate, the long word. It's just an instruction telling us what to do. So I want to find, well, in fact, I should point out, you could break this up. You could write this as the integral or antiderivative of 2 over x minus the antiderivative of 1 over x plus 4. And then you can even bring this 2 out in front. Now, do I think you should do any of this work? Not really. So now I've got 2 times the antiderivative of 1 over x is the natural log of the absolute value of x. I'm not going to write plus c yet. Minus the antiderivative of 1 over x plus 4 is also the natural log of the absolute value of x plus 4. Plus c. And here's something I think is going to save you all some time. Let's find the antiderivative of 1 over 3x plus 1. I really don't want to use a U sub yet. Not because it's not doable, but because it's a longer process than what I think you need to do. So here's the thing. When you integrate 1 over or a constant over a linear function of x, right? Y equals 3x plus 1 on its own would be just a straight line. So if you got 1 over a linear function of x, you're going to get the natural log of that linear function. Almost. So let's ask ourselves a question. And again, you should be ready to, we're going to fix this because the question is this right? Meaning, if I take the derivative of this, do I get back what I started? And the answer is not quite. If I take the derivative of the natural log, I don't really like to write the absolute values here, but fine. The absolute value of 3x plus 1 plus c. When you take the derivative of this, you should just ignore the absolute values and pretend like they're not there, because it works out that way. What's the derivative of the natural log of some stuff? What's the derivative of the natural log of x? Right. So when I say stuff instead of x, you should think, oh, I'm just going to replace the x with stuff. So the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff. But I said stuff, which means we're using the chain rule. So I have to multiply by the derivative of the stuff. What's the derivative of 3x plus 1? 3. I don't have a multiple of 3 in here, right? I'm off. This and this differ by multiplying by 3. So I don't want that 3 to be there. So I really, really need a 1/3. So that when I take the derivative of 1/3 times the natural log of the opposite value of 3x plus 1 plus c, I get 1/3 times 1 over 3x plus 1 times 3. And then the 1/3 and the 3 multiply to 1, and you just get 1 over 3x plus 1. This is what Grant and I and other people who work at the AATC often call a mini U substitution. We could have done a U sub here, and when we talk more about U sub, we will talk about how we do the U sub here. But really, what I want you to know, because I think it's worth your brain space, is that if you were to take the derivative of something and end up multiplying by a constant, let me emphasize the constant part of that, the antiderivative, you're just going to end up dividing by that same constant or multiplying by its reciprocal, if you want to say it that way. So for example, if someone said, what's the antiderivative of sine of 6x? I know that if I took the derivative of that, I would get cosine of 6x times the derivative of 6x, which is 6. So when I take the antiderivative, well, the antiderivative of sine is negative cosine. I should be more explicit though. The antiderivative of sine of some stuff is negative cosine of the stuff. But what do I need to divide this by so that it ends up working out correctly? Yeah, I prefer to write times 1/6, but either way is fine. You can write it like this. You could write it as negative 1/6 times cosine of 6x, which is probably a more standard way of writing it, or you can write it as negative cosine of 6x over 6 plus c. Either way you write it, the derivative of a constant times cosine is negative 1/6. In fact, let's find it. The derivative of negative 1/6 times cosine of 6x is going to be negative 1/6 times the derivative cosine of some stuff is negative sine of that stuff times the derivative of that stuff. And that exactly works out. Negative 1/6 times negative 6 is positive 1, and you get 1 times sine of 6x. So you don't need to do this work, but I want to point out that if you're not sure if your antiderivative is correct, you can always try to check by saying, well, if I take the derivative of this thing, do I get back to where I started? The answer should always be yes. Let's look at one more example here. Let's say I want to do the integral of e to the tangent of x times secant squared of x. Yeah. So here's what I know. And again, I'm kind of cheating this one, to be perfectly honest. This one is probably one where you should actually use the U substitution. But we're going to skip it for now just because I want to kind of, again, talk about the thought process. I know that the derivative of e to the x is e to the x. I know that the antiderivative of e to the x is e to the x plus c. So my guess here for the antiderivative would be something like e to the tangent. Because I know I can't change what's in the exponent, or really whatever the argument of the function is, the inside part of the function, you can't change it. It's stuck. Some people like to describe the e to the, or the square root of, or the sine of as being like a guardian or a bodyguard for what's inside the function. It's protecting it. The stuff inside the function cannot change. So I know I have to have something like e to the tangent of x. And then I might just check. If I took the derivative of e to the tangent, I would get, in fact, let's write it down. The derivative of e to the tangent is, well, the derivative of e to the stuff is e to the stuff times. Thank you. Yes, that's exactly what I'm hoping to hear every time. The derivative of the stuff. And the derivative tangent of x is secant squared of x. That's exactly what we have. So this is good. We just need to slap on a plus c. We'll come back to that. Yeah, we have enough time. We'll come back to that one in a minute here and show how you would do it doing a U sub as well. So let's talk about U substitution briefly here. There's never enough time, but we'll talk about it. So let's say I wanted to find And the problem is all your guys' questions are like definite integrals, right? I feel like most of them are. Yeah, there's a lot of definite integrals. Okay, well, it's fine. So let's say I wanted to find the integral from 0 to 1 of 5x to the 4th times x to the 5th plus 2. I will point out that you could do this easily by multiplying it out. We could totally write this as the integral from 0 to 1 of 5x to the 4th times x to the 5th is 5x to the 9th. 5x to the 4th times 2 is 10x to the 4th. We can anti-differentiate and get 5x to the 10th over 10 plus 10x to the 5th over 5 from 0 to 1. I'd probably simplify that and write it as x to the 10th over 2 plus 2x to the 5th from 0 to 1. And then I plug in. Plugging in 1, you get 1 divided by 2 plus 2 times 1 minus, you should always check when you're plugging in 0. Most of the time when you're plugging in 0, you get lots of zeros, but you might not always. If you got like cosine of 0, that's 1, or e to the 0, that's 1. So just don't just assume everything's going to be 0 when you plug in 0. It will be here. You get 0 divided by 2 plus 2 times 0 to the 5th, but it's good to think about what's happening. So here we get 2.5, which is 2.5, or as a fraction, 5/2. Please don't write 2.5. Nobody likes that. That's not true. Everybody likes that, but no math professors want you to write that as your answer because I don't know. It's just people might think you mean multiplication, and 2 times 1/2 is not the same as 2 plus 1/2, which is what 2.5 actually means. So we don't usually write mixed fractions for whatever reason. Let's talk about how we do this doing a U substitution. So the idea with a U substitution is you're trying to pick U equal to something so that the derivative of U also is in your integral. So here, the choice for U that I would make would be letting U equal x to the 5th plus 2. Because the derivative of U is exactly 5x to the 4th, which I have in my integral. So what I can do is I think of it as like a translation problem. I'm translating this integral from the language of x to the language of U. And I can't do a half-assed job. I can't leave any x's behind. Everything has to become u's. No x's allowed anymore. So if I start rewriting this, my integral of 5x to the 4th times x to the 5th plus 2 dx, there's like 3 different kind of ways of doing what I'm about to do. My preferred way is to multiply both sides of this by dx. And write this as du equal to 5x to the 4th dx. And it's not going to be necessary for this problem, but then I usually ask myself, what do I have to do to manipulate this right-hand side so that it looks like something I have in my integral? Well, in this case, nothing. I don't have to do anything to this because I actually already have a 5x to the 4th times dx. If you prefer, you can write this so that the 5x to the 4th is next to the dx, but that is totally unnecessary. So that's going to be replaced with just du, and it is exceptionally important that you make sure the dx changes into du. It can't just magically happen. We have to say, oh, du is actually equal to 5x to the 4th times dx. So that 5x to the 4th times dx is going to get replaced with du. And my x to the 5th plus 2 is going to be u. So then we rewrite our integral as the integral of u to the 1st, if you want, times du. Now we anti-differentiate. We're going to get the antiderivative of u to the 1st is u to the 2nd over 2. And yeah, I'm going to do this one kind of the way I don't usually do it, which is then we can substitute back in what u is equal to. Oh, I'm not going to write a plus c because this is a definite integral. So eventually we're going to plug in the limits of integration. Just give me a minute. That's going to be x to the 5th plus 2 squared over 2. I don't really want to multiply that out, but I'm going to multiply it out just so you can see. If you multiply this out, you get x to the 10th plus 4x to the 5th plus 4 all over 2. Which if we simplify, is equal to x to the 10th over 2 plus 2x to the 5th plus 2. And notice, and I do think it's worth noticing, notice that my antiderivatives, are they the same? Are they? Who thinks they're the same? Thumbs up. Who thinks they're not the same? Thumbs down. Are they exactly the same? Yeah, good. I'm seeing some thumbs down. They are not exactly the same. Are they the same enough? Yes, they are. Because they differ by this constant plus 2. But it's totally okay that if you happen to do an antiderivative and using a different method and your answer is different than someone else's by 2 or 3 or pi or some other constant, that's totally valid. The antiderivatives can differ by a constant. But now we're going to do the evaluating. So this was the integral from 0 to 1. From 0 to 1. Now I want to point out here, we shouldn't write 0 to 1 over here because we're not going from u equals 0 to u equals 1. We're going from x equals 0 to x equals 1. And this would be from x equals 0 to x equals 1. And then this, you can actually go from 0 to 1. If you plug in the 1, you end up getting 1 plus 2 squared over 2 minus, if you plug in the 0, you get 0 plus 2 squared over 2. That ends up being 3 squared, so 9 halves minus 2 squared is 4 halves, which ends up being 5 halves. So you get the same result either way you do it. Now, here's the point. Sometimes you can't do an integral like this without doing a u substitution. For example, I know we're like almost out of time here. We'll definitely talk more about this. But let me just show you one more thing. Let's say I wanted to do the integral from 0 to, sure, 0 to 2 of, that's going to be terrible. Fine. Yeah, sorry. Let's say we have x squared times x cubed minus 7 to the 99th power. Could you multiply that out? I mean, sure, it's technically possible. Should you? No, you definitely should not. That's so many terms. It's like literally 100 terms. No one should multiply that out. It's very, very not right, the right thing to do. Instead, what we should do is we should do a u substitution. We should let u equal, here's a good way to choose u. There's two things to think about when choosing u. You want to try to pick u equal to something whose derivative is also there. And a good place to look for u is stuck inside another function. So u is the thing that's inside the sine function, or the exponent of e to the something, or the thing that's being raised to a ridiculously high power. So I'm going to pick u equal to x cubed minus 7. And my derivative, my du dx is 3x squared. Do I have a 3 times x squared? Not exactly. Do I care about the 3 part? Not really. What I would do here is I would fix it. I would say du is 3 times x squared times dx. And then personally, I would multiply both sides by 1/3 and say 1/3 times du is equal to x squared times dx. And then when I rewrite this, and again, I do like to kind of rewrite the order of things so that you can see the du nicely. I have the integral from 0 to 2 of x cubed minus 7 to the 99th times x squared times dx. And then the x squared times dx, that's equal to my 1/3 times du. My x cubed minus 7, that's my u. So this integral, and I know it's 3 o'clock, so if you need to go, you can go, becomes the integral of u to the 99th power times 1/3 du, which I would totally bring the 1/3 out in front. I'll say one last thing and then I'm done. I personally would also change the limits of integration. So instead of writing x equals 0 and x equals 2, I would say, oh, if x equals 0, u is going to be 0 cubed minus 7, which is -7, which is going to be terrible. And if x equals 2, u is going to be 2 cubed minus 7, which is 1. And then the nice thing about this is you don't have to change them back when you actually are finding what the integral is equal to. You can just say, oh, okay, well, I'm going from -7 to +1. So that's going to equal u to the 100th over 300 from -7 to 1, and then you plug in 1, and you get 1 to the 100th over 300, minus you plug in -7, you get a terrible number that I didn't anticipate. Oh, well. I didn't change back to X, and that is totally okay for a definite interval. And it is, in my opinion, the preferred way of doing it. So if you're doing a definite integral and you have to do a U substitution, I would say change everything to U, including your limits of integration. These are X limits of integration here, and we used our choice of U to change those X values into U values. All right, that's all I got for today. We'll definitely talk a lot more about U substitution on Wednesday.